Well, similar to Alexei, I did not give a talk in the COVID years, and so I hope that I did not forget it completely, how to do it. The well-known canonical system is given by the equation 1. Our abbreviation CS for canonical system will be used further in the transparencies. CS class includes such important subclasses as Schrödinger equations, Dirac systems, and string equations. And as already mentioned by Alexei, fundamental results in this field when p equals 1. Yeah. So the Hamiltonian, when Hamiltonian is 2 by 2 matrix function, belong to Mark Krein and Louis de Branches. After their works, there were many interesting further works and developments, and parts of the authors I wrote down here. The list is far from being complete. In the p equal 1 case, normalized Hamiltonians are considered with real valued entries usually. And it essentially simplifies the matter because it comes to one complex valued matrix function, so to say. There is essentially less results, although there are results definitely, for the no less important case p more than 1. And what I will talk about is a canonical system with p more or equal 1, and a Hamiltonian of the form beta of x adjoint beta of x, where beta of x are 2 times differentiable p by 2p matrix functions, and the equality 4 holds. The identity is 4. Systems 3, 4 are complementary to the subclass of canonical systems corresponding to Dirac systems, which we studied earlier. In the case of Dirac systems, the requirement on beta looked like this. And here we have 0. And it is a class of canonical systems corresponding to matrix string equations. And the transformation from this system to matrix string equation is simple, and it is written down here. The requirement that beta is 2 times differentiable means that kappa of x here is differentiable, which is a natural requirement, although one could also develop the work in the sense of distributional systems. And in our work, we use several important results from the book by Sakhnovich on the canonical differential systems. Now we turn to Weyl functions. So we introduce the frame of the coefficients in the corresponding linear fraction transformation by the equation 5, we introduce pairs of meromorphic matrix functions with property J, and Weyl-Titchmarsh functions. The set of Weyl-Titchmarsh functions on the interval 0R is described by these linear fractional transformations, as it is usually done. Functions phi belonging to n of R are called Titchmarsh-Weyl functions of the canonical system on 0R. They belong to so-called Herglotz class and admit Herglotz representation. I remind that we consider this kind of canonical systems, and in this case, mu equals 0, and tau t are spectral functions, spectral matrix functions of our canonical systems, the tau t of t in the representation of the Weyl-Titchmarsh function, in the Herglotz representation. Moreover, there is a one-to-one correspondence between Weyl function and spectral functions, and the same procedure recovers our canonical system either from the Weyl function phi or from the spectral function tau and matrix nu given in 8. And now we give this procedure. As is usual in the method of operator identities, the structured operators S acting in here L2P0R will play the fundamental role. And this operator S is expressed via the spectral matrix function in this formula 9. The structure of the operator S is described with the operator identity, which is given here. Phi sub 1 and phi sub 2 act from finite dimensional space into L2. Phi sub 2 is simply embedding, and phi sub 1 is multiplication by the matrix function phi sub 1 of x. And phi sub 1 of x is essential for us, and it is also expressed in terms of tau and nu in the formula 11. So we have operator S, and we have operators phi sub 1 and phi sub 2. The formula for operator S may be written down in the more simple way, because phi sub 2 is embedding. So instead of phi sub 2 here, we can write identity matrix, and then we have this, and it can be substituted in the formula for S. Clearly, S is non-negative. In fact, it is positive and boundedly invertible. Now we introduce operator P, consisting of blocks phi sub 1 and phi sub 2. And we can already express the fundamental solution of our canonical system. The fundamental solution of our canonical system is given by this formula, where W sub A is the transfer matrix function in Lev-Sakhnovich sense. Well, we have a fundamental solution at the end of the interval. And in the same way, we can introduce fundamental solution in all the points L of the interval. Well, for this purpose, we introduce ortho projector PL, and here we introduce operators P, which is Greek P, and S, PL and SL. Then the formula is quite similar to the formula that we had for the fundamental solution at the end of the interval. And the solution of the inverse problem is given by this formula for the Hamiltonian. The proof of the results above is based on the construction of the triangular operator E, similarity transformation, such that this operator, it is a similarity transformation of the operator A, which is a squared integration. Well, I had to say that it was written, but I did not say. A is squared integration, where we have A. Yeah, here is A. Minus squared integration. So this operator is similar to the operator A, and E is similarity transformation. And we have also this condition, normalizing E. Afterwards, we derive in the proof that S, it is E to the power minus 1 times E adjoint to the power minus 1. So clearly, it is boundedly invertible. Now we come to the semi-axis. The families of Weyl function on the of the canonical system on the intervals are embedded. So if our system is given on the semi-axis, the intersection of these embedded families is non-empty. H of L does not depend Hamiltonian on the choice of R. And introducing Weyl functions as intersections as functions belonging to the intersections of N of R, we derive the solution of the inverse problem on the semi-axis from the solution of the inverse problem on the intervals. And we also have this property which holds for the Weyl functions on the semi-axis, which is also sometimes used as the definition of the Weyl functions. This solution belongs to L2 of H. Well, now high energy asymptotics. The study of high energy asymptotics of the Weyl functions was actively done after the fundamental papers by and seminal papers by Barry Simon and by Fritz Justesi and Barry Simon on the Schrödinger equation. In our case, we have the following high energy asymptotics result. It is written here. And the derivative of phi sub 1 is some analog of the A amplitude for the Schrödinger equation. It is of interest that at least part of the theory, including high energy asymptotics, works for a natural generalization of our canonical system of this form. where J is such that here we have identity matrices, and M sub 1 does not necessarily equals M sub 2. When M sub 1 equals M sub 2, we have the previous case. It is of interest that the operators S which go with this J are not uniquely defined by the operator identity. Moreover, there appears a restriction of phi sub 1 of this form, which did not appear before. And it is very interesting in what it says to us about the corresponding Weyl functions. This question I did not study yet. Well, that is the formula for the operators S. It is complicated, but nonetheless, we have a certain structure in this operator. And now, several words about explicit. I can. Yeah, thank you. Explicit solutions are of interest in applications closely related. Addressing commutation methods and Backlund-Darboux transformation are fruitful tools for the construction of explicit solutions, and we use for this purpose our GBDT version of Backlund-Darboux transformation. And we constructed GBDT transformation and explicit solution for canonical system, but here I think it will be more interesting to talk about certain generalization. That is some analog of canonical system with a rational dependence on the spectral parameter. If 20 is an initial system, a transformed GBDT transformed system of the same structure is determined by a triple of matrices such that a matrix and the identity holds. Here, A, S of 0 and P of 0 are different from what we discussed before. They are matrices. The transformed system, that is transformed Hamiltonian H sub k with tilde, and the solutions of this transformed system are expressed in terms of the generalized eigenfunction pi of t and the matrix function S of t, which is expressed via pi of t. And A is a so generalized matrix eigenvalue. I will not write the precise equation for pi of t. It is something similar to the system which we wrote above. But finally, we turn to the interesting related dynamical system. And this is this system. Its explicit solutions are expressed via pi of t and S of t, which we constructed for the previous system. And from the exponents of the generalized eigenvalues. they have the following form. And now a little bit more about this dynamical system. It can be written down in this form where J is Q-symmetric. And it is of the system is of interest in the Port-Hamiltonian, so-called Port-Hamiltonian theory. In Port-Hamiltonian history approach in control theory, Jacob, Morris, and Zwarte, for instance, used canonical systems. The case of spectral variables, although the Port-Hamiltonian systems are widely studied, is studied quite insufficiently. But in this topic, there is a well-known thesis by Villegas, which considered such system with H sub k just constant matrices. In our case, they depend, H sub k depend on T, and we obtain explicit solutions. And one of the uses it may have in the Port-Hamiltonian theory, it is if we treat this triple and F, which define our systems in solutions to optimize and control our systems in solutions as it is done in the Port-Hamiltonian theory. This is the reference, and thanks for your attention.